All right, for today, we're coming back to, we're in the middle of chapter 9. And in this chapter, we started to look at the concept of atomic orbitals. And we talked about at the very end of Monday's class how quantum numbers ultimately describe these orbitals in terms of their energy and their shape. And so that's kind of where we left things off, talking about, of these 4 quantum numbers, we were most interested and concerned with the 2 that are highlighted here in yellow, because they represent for us those quantum numbers that describe the orbitals themselves. And so just a little bit more information about those before we start using them. One thing that we should understand is that as that energy level increases, as that principal quantum number, the N, increases, so does the energy of the electron. So electrons start at the first energy level, N equals 1, and they can exist at any whole number integer energy level all the way up to infinity, technically. Now, generally speaking, we don't talk much about electrons existing past energy level 7, primarily because once we get past that energy level, we start to have the conversation of whether or not the electron is actually still in the atom or not. But the thing that we should know, there are 2 things, really. The first thing that we should know is that this is definitely an energy increase here. The other thing that we should know is that as we go up, the energy levels get closer to each other. And that's why when we talk about, once we hit energy level 7, energy level 8, energy level 9, those energy levels are starting to get so close to each other in energy that it becomes a real conversation about when is the electron actually part of the atom and when has the electron left the atom. And when an electron leaves an atom, we no longer call it an atom, we call it an ion. So that's the first piece of information that we have to kind of familiarize ourselves with. The fact that our energy levels increase, and when they increase, the energy of the electrons increases as well. The other thing that we need to make ourselves aware of is that that second quantum number, the angular momentum quantum number, tells us the sublevel, so what part of the energy level we are looking at. And each sublevel has a particular name and a particular shape. So the 4 primary sublevels, the 4 primary shapes that we're going to talk about with this course have 4 different names. And the name of the sublevel is just a letter that dictates what kind of shape it actually is. So there is the S sublevel, the P sublevel, the D sublevel, and the F sublevel. And like we saw with the energy levels, what we saw with the energy levels is that there was a general increase of energy as we went from one to the next. We're going to find the same thing with the sublevels as well. The S sublevel is the lowest in energy. The P level sublevel is the next, followed by the D, followed by the F. Each one of these sublevels has its own unique shape. And I'm going to show you the shapes of the first three sublevels here in a moment. So let me just give you a chance to write down what you need to write down. And then we'll peek ahead to what these things actually look like. So starting with the simplest. The S sublevel is a spherical sublevel. The S sublevel basically just looks like a ball. One important thing to note about these sublevels is that as their energy increases, so does their size. So here on this slide, we have two different versions of an S orbital. We have the 1s, so the S sublevel for the first energy level versus the S sublevel for the second energy level. And the thing that I want you to notice here is look at the difference in size. The 1s is considerably smaller than the 2s. Why is it considerably smaller? It's lower in energy. And lower in energy means that it is closer to the nucleus. As our energy increases, so does the ability of that electron to be further away from the nucleus. So what we will find is that regardless of what kind of orbital we're talking about, as that principal quantum number, as that number attached to the sublevel increases, the size of the orbital is going to increase as well. So we're showing it here for S. Understand that it'll be the same thing for P. It'll be the same thing for D. It'll be the same thing for F. Higher energy level, bigger orbital. So that's the S sublevel. For the P sublevel shows a dumbbell shape. So we've got two kind of elongated orbs oriented in three-dimensional space across these Cartesian axes. So think about graphing from math class. There's the x-axis, the y-axis, and the z-axis. These three orbitals orient themselves along those same directions. There's the x-axis, there's the y-axis, and there's the z-axis. Each one of those three can get a designation based upon how it's oriented. So if you're wondering why there are subscripts on those orbitals, those subscripts tell us how they're oriented in three-dimensional space. So the P sub x is on the x-axis. The P sub y is on the y-axis. P sub z is on the z-axis. but they all carry this dumbbell shape. It doesn't matter how they're oriented, they all have this dumbbell shape for that sublevel. For d orbitals, generally speaking, have a cloverleaf shape. You can see that there are 5 d orbitals in total in that sublevel. Most of these d orbitals are arranged in such a way that, again, we see subscripts here. The subscripts tell us where to find them. Now, the difference here between the subscripts for the d orbitals and the subscripts for the p orbitals is about location. When we said p sub z for the p orbital, we meant that it was on the z-axis. In this orientation, what we'll see is that for the ones that are just listed out as xz or yz or xy, the cloverleaf isn't on those axes, but rather between those axes. So all 3 of these shapes feature lobes between the axes. Down here, the x squared minus y squared and the z squared, we see that the lobes are actually on the axes in question. X squared minus y squared, you can see that the x and the 4 lobes are on the x-axis and on the y-axis. EZ squared, we can see that the lobes, the dumbbell-shaped part, is on the z-axis and not between it. So those are the different orbital shapes. Now, backtracking just a touch here. One thing that we can see, one thing that we can focus on is that because of the energy differences between the 4 different shapes, we don't see all 4 shapes in every single energy level. In fact, the energy level itself tells us how many different sublevels are in that energy level. So the first energy level only has 1 sublevel. Sublevel that it has is the lowest energy sublevel, the S. The second energy level has 2 sublevels in it, the 2 lowest in energy, S and the P. The third energy level has 3 sublevels in it, and they're the 3 lowest in energy, the S, the P, and the D. The fourth energy level would have 4 sublevels in it, the S, the P, the D, and the F. If I went further, I would find this trend continue. The 5th energy level would have 5 sublevels in it, the 6th would have 6, the 7th would have 7, and so on and so on. The reason we stop here primarily is because those other orbitals are so high in energy that we rarely see electrons in. In fact, we're going to throw out a term here that's important. It's the idea of a ground state. So when we describe a ground state atom, what we are describing is an atom where all of its electrons are in the lowest energy state possible. So every electron is at its lowest possible energy. That is the ground state for any atom. An excited state, on the other hand, would be a version of the atom where one or more of those electrons is at a higher energy than it should be. Maybe we have an electron that's jumped from the second energy level to the fifth energy level. Maybe you have an electron that has jumped from the fourth energy level to the sixth. There are infinite possibilities for the number of excited states that exist for a given atom. There's only one ground state, because there's only one possible lowest energy configuration. And for the most part, we're going to focus on that ground state, because that's the easiest one to kind of pick on and have some concrete understanding of. As soon as those electrons start moving around, start going in different directions, getting different excited states, it becomes a lot more difficult to try to describe them properly. And so here's where we come to the main focus for today. Our main focus for today, the subject of your post-lecture tonight, is electron configurations. Now, with electron configurations, what we are attempting to do is we are trying to describe the location of all of the electrons in a given atom based upon their location in their own specific orbitals. The key structure to an electron configuration is based upon those two quantum numbers that we talked about. The energy level and the sublevel shape. When we write electron configurations, we're going to describe electrons based upon their energy level and their orbital, and how many electrons fit in that space. And so that's what this designation, NL number, that's what that is referring to. N is the energy level, L is the shape, the number is how many electrons are in that sublevel. So for example, if I was describing an electron that it was by itself in the first energy level, I would describe it as 1s1. 1, because it's in the first energy level. S, because the only sublevel in that energy level is the s orbital. And 1, because it's by itself. Energy level, sublevel, how many electrons fit there? How many electrons are there? Now, like I said, we can use an electron configuration to describe where all of the electrons are in a given element. But in order to do that properly, we're gonna need some more information. We're gonna need a little bit more context to help us to make some sense of this. So let's start here. What are some ways that we can outline these electron configurations? Well, one way is through the use of something called a complete configuration or a full configuration. In this method, you are describing every single electron in a given atom using its designations for energy level, sublevel, and number of electrons. Another way to do this is through the use of something called an orbital notation. What an orbital notation does is it breaks down each sublevel into the number of orbitals that make it up. So as we saw in the pictures, the S sublevel has just the one orbital, but the P sublevel has 3, and the D sublevel has 5. How do we show that? Well, we can show that with these orbital designations that show, okay, the 1s is right here, the 2s is right here, these represent the 2p, this is the 3s, here's the 3p, here's the 4s, and so on. We didn't get too deep into the weeds with quantum numbers, but one of the rules for orbitals is that there are only 2 electrons allowed in any one given orbit. So when we describe the P sublevel as having 3 orbitals, if each one of those 3 orbitals can hold 2 electrons, then there's a total of 6 electrons that can fit in that sublevel. 3 orbitals times 2 electrons in each one. 3 times 2 is 6. If we take that out to the D sublevel, 5 orbitals in that one, 5 times 2, the D sublevel can hold as many as 10 electrons. We probably won't venture all the way out to F, but the F sublevel has 7 orbitals. 7 times 2 would mean that there are 14 electrons that can fit in that level, or in that sublevel, right? What orbital notation allows us to do is it allows us to actually look at each and every electron in the atom and see where they are. Also can give us a sense of whether we have paired or unpaired electrons, which can help us to define some specific properties like magnetism. Aside from those, one thing that we will note is that as we get into more complicated atoms, the electron configurations are going to get longer and longer and longer. Because as we add more electrons, there are going to be more orbitals, more energy levels, and so on. Those gas configurations can give us a reliable shorthand because they can help us to identify what electrons are there as potential bonding electrons and what ones are there as what we would call core electrons, inner electrons that are present but don't actually do any kind of bonding. And so there is a shorthand that we can use, and we will often use especially when we get to atoms that have many more electrons than we want to write out in the whole form. So some general context, some things that can help us as we're building up our electron configurations. One of those things is something called the Aufbau principle. The Aufbau principle, you don't need to know the name necessarily, but you need to know the concept. The concept is simple. Electrons go from low energy up to higher energy. We always start low and work our way up. And so because of this, there is an order to how those orbitals are going to fill up. Now, the orbital order is shown here. Don't worry about copying this down because I'm going to show you an easier way to do it using the periodic table. So don't worry about getting that long list written out. You're not going to use it anyway. But the general idea behind the Aufbau principle is we want to fill our orbitals from lowest energy to highest energy. And so we don't put electrons in that next energy level or in that next sublevel until we fill up the lower energy one first. So this configuration on the right doesn't make any sense because this electron is way higher in energy than it needs. Let's see both of those electrons in that 1s orbital first. Another common guideline here is something called Hund's rule. Hund's rule primarily applies when we are looking at orbital notation. And what we want to draw from this information is something relatively simple. If I have orbitals that are the same energy, because they're from the same sublevel, I'm going to fill them out evenly rather than pairing them up with division. So what this means is when we get to something like the P sublevel, here on boron, that first energy, that first electron fits right there because it has nowhere else to go. Where does the second electron go? Well, by following Hund's rule, we can see that it is going to go into the next orbital rather than pairing up with the first electron. And that's all that this is saying. So again, we really won't see this too much unless we are dealing specifically with orbital notation. But it's still something that we need to know. The final guideline that we want to look at is something called the Pauli exclusion principle. Now, again, we didn't get too deep into the weeds with quantum numbers, but one of the things that quantum numbers tell us is that the electrons within a given orbital are different from each other. The way that we show that difference is by showing different directions with the arrows that we use to represent those electrons. So when I start to pair up electrons inside of my orbital notation, I'm going to see that one is always going to be pointed up and one is always going to be pointed down. And the reason for that is because of this Pauli exclusion principle. Pauli exclusion principle says that every electron is unique. And so even if they are in the same orbital, I need to show some way that the two electrons in that orbital are different from each other. Now, in terms of property, that's called spin. And so common ways of referring to the two electrons are spin up for the up arrow and spin down for the down. So what I want you to do now, if you brought a periodic table with you, now would be a really good time to break that out. If you didn't, that's okay. Try to take notes as best you can, because what I'm going to show you here is how we can use the periodic table to help us to write out these electron configurations and make sure that we always have the right order in terms of how they fill up. So the first thing that I want you to do, if your periodic table does not have numbering down the side, now if you're using the one that I gave you, it should. But if it doesn't, you're going to want to put the row numbers down the side here. Now, why are we doing this? These row numbers represent our energy levels. So we talked about the idea of 7 energy levels. Well, that idea comes from the fact that there are 7 rows on the periodic table. The next thing that I want you to do make some kind of mark over the first 2 columns of the periodic table and label that grouping S. Now, how this is going to work is basically this is a game of chemical battleship where I can identify any orbital, any subgroup by matching the period and the zone that I'm looking at. So here with hydrogen and helium, this is the 1s sublevel. With lithium and beryllium, this is the 2s sublevel. With sodium and magnesium, this is the 3s sublevel. Let's continue on. Mark off the last 6 columns of the periodic table and label that grouping P. Why 6? Well, again, we talked about the idea the P sublevel has 3 orbitals. Each orbital can contain 2 electrons. 3 times 2 gives us 6. These 6 boxes represent the 6 electrons that can exist in that P sublevel. And we can do the same kind of battleship designations. This cluster here starting with boron, that would be 2P. This cluster starting with gallium would be 4P. This cluster starting with thallium would be 6P. Now let's take a mark over the transition metals here in the middle that we have not marked in one group or the other yet. So this block of 10 here, we're going to label that D. Now with D, I want you to make one other note. N-1. Now the reason for that designation is, if you recall from before, the D sublevel starts showing up in the third energy level, right? SPD. So that's the third highest energy. Starts showing up in the third energy level and is in every energy level after that. If I'm marking out from a battleship perspective, I'm seeing 4 NP for that first group of the electrons. And I know that's not right. It's actually should be 3D. So what do I need to do? I need to make a mental note to myself that whatever row I'm looking at, I need to take 1 off of it so that I'm describing the correct orbital. So the D in the 4th row is the 3D. The D in the 5th row is the 4D. The D in the 6th row is the 5D. For completion's sake, we will mark off the last group here, the one that we have not touched yet. This is the F sublevel, and you can make a note here of N-2. Now, the reason we're not going to make that big of a fuss over this is because we're not going to really do any electron configurations that involve F orbitals. So we'll mark it here for completion just so that we know that it's there and we have it, but we're not going to use it very often, if at all. So this is how we use the periodic table to write out our electron configurations. Basically, all that we need to do is we identify an atom, and then starting at the top, we just list out all of the different orbitals and all of the different electrons that are there until we get to the thing that we're interested in. And we're unsure of how many we need to do, we can just count the number of boxes until we get there. So if you forget that the P sublevel holds 6 electrons, so what? Count. 1, 2, 3, 4, 5, 6. How am I going to know that I got the right number? So the best way to do this is through example. Let's take a look at a couple of examples. So for the complete electron configuration of zinc, how do I go about doing that? Well, let's go back a slide. If I'm interested in zinc, right here, I need to start at the top and work my way down until I get to the zinc itself. So for zinc, I have, starting at the top, 1s2. After that, it's 2s2, then 2p6, then 3s2, then 3p6, then 4s2. Then it's 3d. Again, it's 3d because even though this is the fourth energy level, for the d, we take one away. So it's 3 and then d. So a couple of assumptions we can make. We can assume that since this is the ground state and we're at the lowest energy possible, every sublevel leading up to where we're going is going to be completely filled. So I don't need to worry about, okay, well, is this going to be 5 or 4 or whatever? I can assume that all the P's are going to be 6, all the S's are going to be 2 until I get to where I'm going. When I get to where I'm going, then I can count individual boxes to figure out how many it's going to take. So everything's been full up until this point. I get to the 3D, the 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my last configuration is going to be 3D10. Because zinc is the 10th element in that particular group. If it was the 4th element in that group, I would say 3D4. That would be the configuration by way of element. So that's zinc. For the second item, we were looking at argon. For argon, we need to go to here. We still want to count it out the exact same way. So starting at the top, 1s2, 2s2, 2p6, 3s2, 3p is the last designation because that's where argon is. 1, 2, 3, 4, 5, 6. It's the 6th element in that group. 3p6 is its last configuration. The last one on the example page is scandium, Sc. We're going to go through the exact same process. Start at the top. So scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Scandium is in the 3D sublevel. It is the first element in that sublevel. So its last configuration would be 3D1. Because it's the first one in that group. So basically, we can run off of the assumption that everything is full until we get to the sublevel where our element is. When we get to that sublevel, we frame it. So what is it? What energy level? What shape? And then we just count the number of boxes that it's going to take to get to there. Now, for questions like this one, in terms of putting this into orbital notation, all we need to do is just take that configuration that we just made and draw it out in arrow. So 1s2, I would have an up arrow and a down arrow for those two electrons. Remember, anytime I have two electrons in the same box, one of them has to be up, one of them has to be down. So 2s2 would be the same way. 2p6, all of these are filled out. So up and down for all of them. 3s2, same deal. 3p6, all the way filled up. 4s2, up and down. 3d1, I only got the one electron to put in. So I just put it in. General convention tells us two things. First of all, fill the orbitals, if there are multiple orbitals there, fill them from left to right. Second convention, start with up arrows to go up, all the way across, then add the down arrows as needed. In this case, I only needed the one, so first block, up arrow, that's all I would show. If I had two, there'd be two up arrows, one in the first, one in the second. So this is where we're going to leave it for today. I did not quite get as far as I was hoping. So what that means for you is that the post-lecture assignment that is in there, try to do as much of it as you can, but I am going to move the deadline back on that to Friday night, just so that you have more time and as we add more of these other concepts. So try to figure out what you can, lessen your workload for the weekend, but it's not going to be due Thursday night as it says right now in Master. Have a good day.